and that can hydrogen bond. This guy can now kind of hydrogen bond. We describe it as it can receive hydrogen bonds, but it can't donate a hydrogen bond. All right, so technically this is actually less polar. All right. So after we run the plate, we would expect this to be higher than that. Okay. All right, we're going to pull it out of there. We need to look at it and see where the spots are. That's not as simple as it sounds. Okay, when you finish running these plates, they're going to be, it's going to be a white plate. Okay, you won't be able to see anything. So we have to do, we're going to use a special UV chamber for us to be able to visualize this. Okay. All right. But once we're able to visualize it, let's say we've got it in the TLC chamber. And so, product is like, I'm not even going to do ProSpot right now. All right, and then this is one of these things that's pretty straightforward when I'm explaining it on the board and everything like that. And then, actually, you know what? I'm sorry, I don't want to use a different color. That would be nice. And in this situation, we actually do tend to get a color difference. But a lot of the time, we don't have a color difference. And so you just need to go by how far it goes on the plate. Yeah.
How do you know when to pull the...
Good question. Yeah, so...
Because you can't see it, right?
No, you can't. You can't. You will be able to see it because the silica gel, it will look wet. It will look like it got wet. Okay? So you'll be watching, you'll be able to see, you know, okay, now it's the bottom half is wet, the top half is dry. Now the wet, it's called the solvent front, goes higher and higher and higher. You want to pull it out right before it gets to the top. Maybe, I let this one go kind of far, okay? And it can take a while. You want to do it right before it gets to the top, and then I think the instructions tell you, take your pencil and make a little mark here. Okay. One other thing I forgot to mention, when you make this mark with your pencil, do it really lightly, with a light hand, yeah? You don't want to dig a trough in here, and you will, if you put any pressure on the pencil, you will chip away all the silica gel that's right there. Okay. All right, so let's say we take it out, we put it in our special visualization chamber, and we see this. So as I was saying, this is one of these things that when I explain it on the board and stuff, okay, I think I got it. It just, then when they're out doing it themselves, they get a little bit messed up. And I'll try to forewarn you where that happens. Okay. Now, I've given you very little information, but I'm going to test you anyway, because you guys are the brightest ones I have. What can I conclude here if this is what I find when I'm looking in the visualization chamber? If it looks like that, what's a logical conclusion? Nothing's definite. Nothing happened. It's unreacted starting material because my reaction crude gave me one single spot. Doesn't have to, by the way. You know, a lot of time in research it gives me 10. That's not good. But it gave me one single spot, and my one single spot lines up perfectly with starting material. Okay. Now, here's one place where students, when we get away from the pre-lab talk and we're doing it ourselves and stuff, get a little bit fouled up. You might be looking together at your TLC plate and might say, okay, do you have any indication? Do you have indication that you made product? Is there product on your TLC plate? I go, yeah, it's right there. You know, no, that's the store-bought stuff. We gave you. You didn't make this. You only made this stuff. It's in this lane, and we actually do call these lanes. You only made this stuff. Okay. Of course, there's product on the plate. We put it on there. We knew we were putting it on there. Does that make sense? Oh yeah. All right.
Wait, so Dr. Logan,
So the first reaction is what we have. The second one is what's in the hood with what we started.
Sorry, I didn't get past after work.
Oh, oh, I'm so sorry.
See, that's another reason just to go with Gideon.
Sorry. I have you guys in like, okay, sorry. So the
It happens all the time. So what now?
The reaction is what we have. The starting material is what you gave us, which is what we started
Yep.
with. The second reaction is what?
Is the reaction, but we put it spot, and notice I made my
Oh,
spot
extra.
bigger. I made it bigger, yeah.
Okay, and then
Yeah.
the product is our sample, and then
Yeah.
the
And this is really because sometimes what ends up happening, sometimes you might do it, and it comes out like this, and it looks like that. And that's because, oh shucks, it wasn't as concentrated as I thought. And I can hardly see if I made anything. I don't know. There's hardly anything there. I better redo the TLC plate. No, you don't have to do the TLC plate because you did a different lane where you did it harder, where you or did it more. Make sense? Okay. Now, Billy has run his TLC plate, and this is what Billy got. What should Billy include? Or what does this suggest?
there's something new in the reaction,
Yeah.
different than what we started with.
Yeah. How many compounds are in my reaction crude? There's 2. Okay. And there's an indication that some of it is leftover starting material. Okay. Now, why do I keep on saying, why do you keep saying indication? Why don't you just say there's leftover starting material? Because if 2 things line up on TLC plate, that is good evidence. It's like, what do they always use in criminal cases? It's circumstantial evidence. And circumstantial evidence that they are the same. But it's not definite. Because multiple compounds in the world can have the same elution distance as each other. Okay? So it's not definitive. However, if 2 spots go to different places, that's definitive that those are different compounds. Okay? If they were the same compound, they're in the same chamber on the same plate, they would have gone the same distance. Does that make sense?
So this is kind of like inconclusive.
Oh, what?
This is kind of just like inconclusive.
No, it's not that it's inconclusive. I mean, it certainly suggests, what I'm just trying to imply that you have good evidence that you have leftover starting material, because it lines up with the starting material to the best of my drawing ability. Lines up with the starting material. Okay. You also have good evidence that it's product, but it's not definitive. Neither of those conclusions are definitive. Okay. I mean, sometimes we run TLC plates, and you get that. Okay? I have definitive evidence that I have made something that's different from starting material and different from product. If it was the same thing, they would have gone to the same place on TLC plate. So when things line up, you have good indication, but not proof. Perfect proof. If things don't line up, you got perfect proof that they are not the same thing. Make sense? Okay. The last thing I'll explain is the co-spot. Here's what happens, and it's a good example to introduce co-spot because this really happens with acetyl salicylic acid and salicylic acid. And that is, let's see if I can do this. They are just hair different from each other. Okay? And so what you can sometimes get is, what if now in your reaction, What if you get one spot that is which is it? You got no idea, right? I mean, it's like, oh, I don't know. So, what you can do is if you put co-spot, and we're doing co-spot with starting material, we could do this, and we've put starting material on purpose there. And what if now, at the end of our TLC plate, we see a figure 8? What do we know? Conclusive. We know that ain't starting material. Why do I know that? Because it made a figure 8 here. Made 2 different compounds here. If it was starting material, I would put the starting material on top of starting material and I would have made one spot. Does that make sense? Co-spot it's advanced TLC. I'm a synthetic chemist. This is technology from the 1800s, and when we're doing research, doing organic synthesis and stuff, we do 10 to 30 of these a day. It's amazing. It's so quick and dirty to find out a little bit of information about what happened in my reaction. Okay. Oh, almost forgot something important. We like to be able to quantify. Okay, because sometimes maybe we don't have acetyl salicylic acid. Okay, but we want to look up at somebody else's when they did their TLC, and we want to see, oh, okay, did it travel as far as the literature value? Well, how are we gonna compare apples to oranges? Yeah. What you do is you figure out your RF. Call this retention factor. And this is, so every spot can have an RF. Okay. So this is the distance, maybe probably in centimeters. I don't know, whatever ruler you happen to have. Distance of your spot. Okay. Distance eluent. Is it E? Shoot. Yeah, that's right. Sorry, I'm a little lexic dick, so sometimes I feel better. Okay, so all you do to figure out the RF of any of these spots, let's figure out the RF of that, is I measure this distance in centimeters. Okay? And then, like you said, we want to make sure we know when we pulled it out of the chamber, I measure that distance. That's the eluent distance. And that will give me the RF of that. Okay? And then I could, if I didn't happen to have the product, I could refer to the literature. What is the RF? It's got to be the same eluent. You have to use the same eluent system. Okay? Okay, does that make sense? Questions about that? Okay. Sorry, there's a lot here, but actually what you were physically doing today doesn't take that long. All right, I'm going to move these folks. Wait, we're still going, guys. I still got more to do here. Okay, so. Sorry. Social distancing. Okay, so as I said, when you pull this out, you'll see your pencil line and the little RXN, and you'll see that. This will be blank. Okay. All right. Who gets 1,000,000 bonus points today? We're going to shine UV light on this thing. All right. And this is impregnated with some stuff that fluoresces. So when I turn this dude on, and we want to do short wave. Oh, boy, that's dim. It fluoresces green. See if the folks at home can tell that. Okay, it fluoresces green. All right? And that's just because the silica gel is impregnated with a material that fluoresces. Remember, absorbs at one, promotes, okay. Is that clear? Okay. Now, this is UV light. What did we say about a molecule? What property, what structural characteristic does a molecule need to absorb UV light? Bonds. It involves bonds.
The E photon?
It's absorbing photons. These are all true. Alternating double bonds. If you have alternating, well, look at salicylic acid and acetyl salicylic acid. They have alternating double bonds around that benzene ring. Okay? So what things that absorb UV light do is they absorb the light at that area. So the whole plate is neon green, except where there's a chemical that absorbs UV light, and then it's a dark spot. Okay. One of these, I think it is, I forget if it's a starting material product, actually ends up giving you slight different fluorescence. It fluoresces itself, and it's actually a little bit helpful in analyzing your TLC plate. It's not just dark. It's dark and it also kind of fluoresces a little bit. It's unusual, actually. Most compounds, it just gives you a dark spot. Whole thing's green, except where there's compounds. All right. In the olden days, we used to circle these things with a pencil, and then we would draw it in our notebooks. What I think is much more useful now, and in research we do this, everybody has a very high resolution camera in their back pocket right now. Okay, and it's very different from 10 years ago. All right, so you've got that guy, snap a picture of it so that you can analyze it when you're home and looking at it. All right, reminds me of something. A lot of these TLC plates are going to be really hard to understand. This is unfortunately, this isn't one of these dramatic TLCs where, oh wow, the product and the starting material are really different. That's nice for a beginning TLC. But this is a great lab to do for the first lab, so we wanted to do it. So unfortunately but we'll have other ones when we make methyl eugenol. That's a better difference in TLC plate. Okay. And so your TLC plates may be really hard to read. That's why if you notice in the worksheet, we just want you to do the best you can with your TLC plate in terms of analyzing it. But in the worksheet, there is a picture of one where it did work out pretty nice. They separated nicely. And so you need to analyze that. I wanted you to have an opportunity to analyze one where it was relatively clear. But you got to look at it on your computer screen. I think the worksheet says that now, actually. Because if you print it out, now it's in black and white, it's really hard to tell. Okay, so look at it on your computer and go, oh, okay, yeah, I see evidence of starting material, I see evidence of product and stuff like that. Okay, make sense?
But isn't it the reason why we mark it with a pencil, like circle it, is because the solvent still moves right after we take it out, right? Or does
No, the solvent doesn't really move. The solvent evaporates.
No, the lines move.
When we read, it said that the little spots would start changing. They could get bigger after those lines, and so we needed to mark it, but taking a photo will help.
Yeah.
Yeah, but how do we calculate our RF values from our picture from the phone?
A couple different ways. Even though it's a picture you're taking with your phone, yeah, and now it's on your computer screen, and I don't know, you're a gamer, and you have some computer screen like that. The ratio is still going to be the same, right? RF is a ratio, right? So yes, this is now 2 feet that the thing traveled. The eluent traveled 3 feet. Okay? You can also mark it here and figure out your RF. You could do that here in lab. That's a perfectly good idea. Okay. But as long as you take a picture that's not distorted or something, then you should be able to read your RF off your computer screen. Does that make sense? Okay. One last thing that I need to explain to you guys, and that's taking a melting point Okay. That. All right. Almost done this. All right. These will get much shorter, I promise. Doesn't help that I can barely breathe. Okay. So now we want to take a melting point of our stuff. Melting points are really nice. They tend to be fairly consistent, so you'll have a good idea. It depends how carefully you do them sometimes. All right. So now we're not using the capillary tube. We are using the melting point tube, and that's the one that's thicker and sealed at the bottom. Okay. And so what you want to do, I'm sorry, got my back to you. You've got your watch glass, right, of your material. You take the open end and you just shove it down on there so that a little bit gets stuffed up into this melting point tube. Okay? The less the better, actually. Okay? It hardly takes any. You're going to be looking at it under a magnifying glass, essentially. All right. Now you invert it so that your sealed end is on the bottom. You want your material down by the sealed end. How do you get it down there? You take this fancy apparatus, okay, and you bounce it. Sometimes it'll work on the first try, sometimes you're going to do it a couple of times. Okay? All right. Then, okay. We've got two melting types of melting point apparatus. We've got the older ones, okay, which sort of are in two parts, and then we've got the newer all black ones there, okay? So you put your sealed side down, you put your tube in here, and there's a little slot in front, okay? You don't put it in this chimney here. Students are always tempted to do that. There's a little slot in there, and then when you turn this guy on, after it's plugged in, now you can actually see down, you can see your compound. You can actually twirl it around to see that you're actually in there. Okay? All right. And then what this dial does is, this thing's going to ramp up in heat. This decides how fast it ramps up in heat. I forgot to look up the melting point of aspirin. It's in your book. What? Anybody got it? No. Shoot. Anybody got any idea?
135 to 136
Okay.
degrees Celsius.
Beautiful. 135. So for a 135, I would set this on 4. Okay? You don't want to be here all day. All right? And then you're looking at it in this sort of magnifying glass. And you're just looking at the crystals. And as soon as you first start to see some moisture around the crystals, it's called sweating sometimes. As soon as you first see the crystals sweat a little bit, that's the beginning of your melting point range. Okay? When you're getting a melting point, don't ever give a single number, even though the internet gives you a single number. Always give a range. Okay? We started to see it sweat, and then when it's totally liquid, that's the end of the range. Make sense? Okay.
So, aren't we putting it in a solution when we put it in that, or is it a solid for this part?
No, it's a solid for this part. If you put it in a solution, then it's dissolved. You can't watch it melt, right? Yeah. And then for these guys, and there's instructions on this one here. On this one, what you'll do is, there's two things you need to follow these blue instructions. I won't go through them, it'll take too long. But you put it up in this little white slot up here. Okay, that's where it goes. And then you're going to have to put in 2 bits of information. You got to put in what you think the melting point should be. You think it's going to be, what do we say, Kara, 135?
Yeah.
135. Okay, so you're going to put that in. So it has an idea of how to ramp the temperature now. And then you're going to want to, and then it'll ask you, should I ramp it, gosh, what is it? It's like 1 degree per minute or 10 degrees per minute. Do 10 degrees per minute. Okay, do the math. If you have to go from room temperature to 135 at a degree per minute, it's going to take you a long time to do your melting point. Okay, later in the semester there's a fancy way where we can